Hi everyone, my name is Callum Marshall and I'm here to discuss legacy code, what it is and what we can do about it. First, a bit about myself. My name is Callum, my pronouns are he, him. I was born and raised in the UK and moved to Japan about 2 years ago. Both before and after my move, I've been working for a UK-based IT solutions company called Core UK Limited, first as a developer and then as an analyst. And I'm now training to be a full-stack engineer as part of Chrysalis' cohort CC23. So moving on to the talk itself, I'd like to break it down into 4 sections. First, I'd like to provide a definition for legacy code. Second, I'd like to explain the methodology for dealing with legacy code. Thirdly, I'd like to discuss how we can prevent our current code from becoming problematic legacy code in the future. And finally, I'd like to finish with a brief conclusion at the end. So first, a definition of legacy code. What is it? What do I mean by it? Is legacy code simply code that is old? Is it code that is no longer in use or archived? Is it code that was written by your developer ancestors who have long since moved on to greener pastures, aka another company? Personally, I define code as legacy if it has some or all of the following attributes. Unsupported language. The team or company who designed the language no longer provide active updates to resolve bugs or modernize it. An example of this would be Visual Basic, which was created in 1991 and declared legacy in 2008. Improper version control. So the code is improperly version controlled. It may have been written in a time before proper version control was common practice and is sitting in a random directory or a legacy version control system which can be susceptible to corruption. Third, inherited code. So the code has been written by developers who are no longer at the company, possibly separated by at least a few generations of developers so that no one at the company has a deep understanding of what the code does and why. And finally, in need of refactoring. It is code that needs updating to modern standards, for example, reformatting or best practices. So, is all old legacy code problematic? Calling back to Visual Basic, as stated in the previous slide, it was developed in the 90s and declared legacy in 2008. This is actually not that old for a programming language, so we can intuit that age can't be the only factor. After all, we have many languages older than Visual Basic but are still in heavy use today. C and SQL still have ample use in their specific niches. C is still taught in computer sciences courses around the world, and SQL is still very much the relational database language of choice. So when exactly does legacy code become an issue? I believe legacy code becomes an issue when it is too expensive to maintain. Quite often, companies have to shell out a ton of money to highly specialized contractors because most of the workforce that use the legacy language the code is written in have retired. We see this more and more with COBOL developers. Secondly, new developers aren't interested in working on it. Equally, due to its perception of becoming obsolete, the language the legacy code is written in is no longer appealing for new developers. They are less likely to devote serious time to learning a language that is perceived as dead or dying. Thirdly, the code is now vulnerable to modern security breaches. For example, a security vulnerability could be discovered, leaving you exposed to attacks like the one seen in the data breach of the US Office of Personnel Management in 2013 to 2015. Forgotten purpose, when no one currently at the company knows how the code base works and why. It may take a given developer a long period of time just to understand what the code does, let alone make any necessary improvements or fixes. This is amplified when it is written in a language that they don't know. And finally, spaghetti code, when the legacy code has become increasingly spaghetti-like. This tends to occur because it is often more expensive in time, money, and resource to implement a good solution, which would decrease our technical debt, and to incorporate a hacky quick one, which can often increase our technical debt. What do I mean when I mention technical debt? So technical debt describes what results when development teams take actions to expedite the delivery of a piece of functionality or a project which later needs to be refactored. In other words, it's the result of prioritizing speedy delivery over perfect code. So why is it a debt? Because often you have to pay it back later. The code base becomes more and more messy and inefficient and will usually need to be addressed at some point in the future. The longer you leave it, the messier it gets, and our debt interest grows and grows. Therefore, we should always do our best to minimize our technical debt. A good developer always pays their debts. So here's a quote from Michael Feathers on legacy code, which can sum up the experience of working on it quite nicely. Legacy code. The phrase strikes disgust in the hearts of programmers. It conjures images of slogging through a murky swamp of tangled undergrowth with leeches beneath and stinging flies above. It conjures odors of murk, slime, stagnancy, and offal. Although our first joy of programming may have been intense, the misery of dealing with legacy code is often sufficient to extinguish that flame. So we've discussed what legacy code is. Let's talk about how we can address it. I'm going to suggest we use 4 principles to help us address our legacy code. Redocument. Create or update any documentation you have on your legacy code. Retest. Test that the code behaves in the way you expect. Often there can be some hidden quirks that take you by surprise. Refactor. Refactor your legacy code so that it is easier to read and understand. And finally, rewrite. If you have the chance, rewrite your legacy code in a modern language to extend its lifetime. I'd like to go into some detail for each principle before demonstrating how we might implement them. So, our first principle is redocumentation. Why is documentation important? Good documentation can be incredibly useful. We can use it as a tool to onboard new developers quickly, potentially reducing the amount of face-to-face teaching time required of our senior devs. It can also serve as a memory aid. How many of us have forgotten what a code does in as little as 6 months later? We can pass it to it's useful for non-technical people. We can pass it to non-engineers to help them understand what the code does and why. And finally, it can provide context for design decisions. Sometimes the original design of something can shift quickly to align with new customer requirements, so the end product can end up looking quite different from the original design. Documentation can provide the necessary context for why the code looks the way it does. If we don't have good documentation provided for us, then we may have to create it ourselves. This can be a daunting task. If best practices have not been implemented, then the limited documentation we do have could be long out of date, missing, or just plain wrong. So, the next principle is retesting. Why is testing important? I have another quote from Michael Feathers. Code without tests is bad code. It doesn't matter how well written it is. It doesn't matter how pretty or object-oriented or well encapsulated it is. With tests, we can change the behavior of our code quickly and verifiably. Without them, we really don't know if our code is getting better or worse. Most developers are now aware of the importance of unit tests and integration tests. Having effective unit tests makes changing code simpler. Breaking changes will be highlighted immediately. Also required are high-level functional tests, as they can guide understanding of why the code was implemented and are useful for QA purposes, testing how closely code aligns with business requirements. The next principle we need to consider is refactoring. Refactoring means changing the general structure of the code without altering its functional behavior. Good refactoring makes for clear and concise code. Some examples of refactoring are altering coding style to match consistent guidelines, replacing inefficient or redundant code. Altering the code can always carry risk if it's not properly tested. Modern languages often support testing frameworks, which make refactoring a lot simpler. So the last principle is rewriting. It would be lovely if we could rewrite all the bad or outdated code we've written. But this can be prohibitively time-consuming, expensive, and risky. The relevant stakeholders must balance the pros versus the cons. A couple of examples of why we might go for a rewrite are: We are paying some highly expensive contractors every year to patch hacks which become more and more chaotic. At this point in time, it is worth spending the money on refactoring or rewriting in order to prevent this ongoing cost. Alternatively, we have discovered a security vulnerability in our codebase that fortunately has yet to be exploited. If it was to be exploited, then the consequences to us and our customers would be devastating. We should get ahead of it now while we have the chance and perform a rewrite. So now I've gone over the importance of the 4 principles. To demonstrate them in action, I've created a simple demo using C. So, while combing through my codebase, I've stumbled across a mystery legacy function that appears to perform a calculation. Let's have a look at the code. Okay, so on the surface of this, I don't really understand what this function is for. It appears to be a calculation. So we have some variables at the top. We accept some input here. And then we perform a calculation at the end and return it. Okay, so it's still not very clear. What should we think about next? So our first principle is redocumentation. Let's see what documentation we have available. Okay, so we have a readme.txt. Maybe this has some important information we can use. The documentation states that the purpose of this function is to calculate the necessary escape velocity of an object leaving Earth. That appears to be it for the documentation we have available right now. We have to remember to keep that up to date. But first, let's test our function. Okay, so I enter some values. So often legacy code does not have automated testing, which means you may have to deploy your code to a test environment so you can run some functional tests. This can help you to understand the behavior of the code base, identify any performance bottlenecks, as well as highlight any quirks that are common with spaghetti languages or legacy code. In our case, we have no test suite to rely on, which is why I ran it in VS Code. So the value that we got was 11,186.007443. A previous Google search informed me that the expected value is approximately 11.2 kilometers per second. Interesting. So our function returns the escape velocity in meters per second. We should feed this back into the documentation. So here is an updated version of the original README, which I've added some information I found relevant. I'll leave the code comments until the refactoring stage. So I start with a brief description of the function. I give the basic form of the equation that's used, and I give details on each variable, as well as their units of measurement. In a perfect world, we would rewrite our code in a modern language using modern practices. This is rarely possible. Often, there is not the time available to accomplish a rewrite, as replacing legacy code can be sidelined by more pressing demands. But refactoring the code, without altering too much of the behavior, can be a good first step in rewriting the solution. You want to avoid introducing breaking changes, but adding comments to the code, proper indentation, are some good examples of low-risk, easy refactoring. Be aware that any refactoring action carries risk, so you must set aside enough time to fully test your changes to be confident that you haven't introduced any new bugs. So I prepared a finished file that I've added some very basic refactoring to. So as you can see, side-by-side comparison, I've replaced the single declarations, shorthanded them by using commas, and I've removed some of the variables that I know and I'm confident in aren't used in the final derivation. For example, the kinetic energy and potential energy calculations here are relevant to the physics derivation, but aren't used in the final calculation. I've also added comments just so it's clear what each value is. So let's double check that my new code works. Okay, so I get the same result. That's a good sign. Next is the rewriting stage. For our simple function, a complete rewrite is probably not necessary. But to provide an example of rewriting, I have a JavaScript code snippet just to illustrate. So here we have our function, which I've made slightly more generic by accepting two arguments representing the planet mass and radius. I've named my variables to be more descriptive rather than the physics notation, which were single letters. So let's see if I get the same result. Okay, I do, and to a higher degree of accuracy. So that was a successful rewrite. So we've addressed how we might tackle some existing legacy code, but how can we future-proof the code that we write today? It's simple. Apply the same principles we used to address legacy code to writing our future code. We must keep in mind that our code will probably be replaced in the future, and we must accept the possibility that this could happen later than it should. The four principles are document, test, write, and refactor. So we've already gone through why documentation is important, but here is some general advice to keep your documentation high quality. So first, log design decisions. Make sure to keep a log of design decisions made. Second, keep track of internal and external correspondence to avoid miscommunication. This applies to both internal, so within your development team, and external to avoid obviously miscommunication with the customer. Third, make it accessible. It needs to be in an appropriate location so that it can be accessed by those who need it. And finally, keep it up to date. Documentation should always be aligned with the functionality it is describing. So for testing, I won't go into too much detail, but I would recommend using test-driven development if you are able to incorporate it. Examples of unit testing frameworks for JavaScript are Mocha, Chai, and Jest. We should aim for as much test coverage as possible. For writing functional or integration tests, there are tools like Zephyr Scale or X-Ray, which are a couple of Jira test management components. Your functional tests should ensure code meets business requirements. Finally, development and design. The higher quality our code is, the less maintenance or rewriting that should be required. When designing our solution, we should try to go for the best solution, which may not be the quickest one. We want to make sure we don't increase our technical debt where possible. Then, when we develop against the solution design, it is important that the code utilizes proper design principles, such as solid, dry, and KISS. Modularity can also be super important, as it means that code can be easily replaced in the future. Refactoring. So if you keep in mind that your code may be read as many as several years later, it can help you to remember how important well-factored code is. If your company has style guidelines, then you should stick to them. If you refactor with readability at the forefront of your mind, you help out the people who follow you massively. Generally speaking, if we follow best practices and coding guidelines, then this step should already be a natural part of our project process. As a bonus step, it can be helpful to utilize static analysis tools. These often provide a way for you to automatically gain analyses of your code base. They aren't perfect, of course, but they can resolve some common issues, especially pertaining to security, like SQL injection or memory leaks. So to wrap things up, I'd like to show you a quick timeline of the lifecycle of legacy code. So we start with some legacy code that we want to change. First, we ensure that the documentation is up to date, and after conducting our tests, we can ascertain its behavior. Now, we refactor our legacy code as much as possible until we get to a point where the legacy code can be rewritten or archived completely. During our rewrite, we follow best practices and follow our company style guidelines so that our end product is clean, maintainable, and easily replaceable. In conclusion, we might not always be able to rewrite legacy code from the get-go, but there are certain steps we can take to chip away at the problem bit by bit. When we do get the chance to rewrite our code, we should always keep an eye to the future to keep us from repeating the mistakes of the past. Thank you for listening to my tech talk. Thanks to Felipe for helping me develop this presentation, and thanks to Chrysalis for the platform. If you'd like to contact me, please reach out to my Gmail, which I've added to the slide. Thank you.